Scholars, this is a quote from your textbook. What has always distinguished calculus from algebra is its ability to deal with variables that change over time. So you, in geometry class, learned a whole bunch of formulas for volumes and surface areas and areas, perimeters, and you learned how to use algebra to take that equation. Maybe you solved it for a different variable. Maybe you substituted values in to find a volume or a perimeter, but you never had a chance to use a formula like that. You can see my formula is peeking down from below. You never have a chance to use a formula like this, the formula for the volume of a sphere, to think about a sphere that is actively changing volume. This is what calculus can help us do. It's a big deal. It really is a big distinction between calculus and algebra. So, you could imagine somebody blowing up, making a sphere and making it to increase in volume, like you're blowing up a soap bubble or blowing up a balloon. Because of the air you're putting in, the volume is increasing. And we can, with calculus, talk about how fast that volume is changing. So this new topic, it's called related rates. And it's really just a big application of implicit differentiation. So we're going to review implicit differentiation super fast. Okay, so we talked about here, this is the equation for a circle with a radius square root of 17. And you could find the derivative. We could find dy dx for this curve and use it to think about the slope of this circle at any point on the circle. And we talked about using implicit differentiation to do that. Because when we take the derivative of both sides with respect to x, it's no problem when we're taking the derivative of x squared. But when it's time to take the derivative of y squared, how do we take the derivative with respect to x of something that's not even a function of x? So the derivative of y squared with respect to y is 2y, and we use the chain rule to find that missing link to connect the derivative of y squared to the derivative of y with respect to x. So that missing piece in this case is dy dx. So 2y dy dx plus 2x equals 0, and I can isolate dy dx. What sometimes stops students up when we get to related rates is that we're not going to even very frequently use x and y. So just notice that I could do this exact same problem. All the algebra is the same, all the calculus is the same. I could change those variables and the process is still the same. So p squared plus t squared equals 17. If I want to find the derivative with respect to t, so if I want to find dp dt, I'm going to differentiate both sides with respect to t. Process is exactly the same. The derivative of p squared with respect to p is 2p. And in this case, the missing link is going to be dp dt. If I'm differentiating with respect to t, the derivative of t squared is simply 2t. Same process, different variables. So don't let the variables throw you off because you'll be seeing some variables like the ones we don't typically use. All right. All right, so my screen is super big here. Let's get this all cleaned up. So go back to the soap bubble. The rate at which the volume is changing, the thing that's making the volume change, at least in this case, is you adding the air into it. So it's changing over time as you add air into it. So most of the time when we talk about related rates, we're going to be talking about the rate at which something changes with respect to time. It's not always time, but a lot of the time it's time. So if I say the rate of change of volume with respect to time, and I think about how I would write that, I would write dv dt. So this is what we're aiming for, is an expression for dv dt, and I'm going to find that by using implicit differentiation. I'm going to scoot up here. Okay, so if I want to take the derivative with respect to time of v equals 4/3 pi r cubed, the derivative of v with respect to time, I'm going to call it dv dt. The derivative of 4/3 pi r cubed with respect to time, I don't know yet. I'm going to have to take the derivative with respect to the variable that is there, the r, which would be the 4/3 times the 3 comes down to the front, times the pi, times r to its new exponent, which is 1 less than 3, which is 2. And then I'm going to have that link. How do I sort of translate? How do I convert from that derivative which I just took with respect to r and the quantity I really seek, which is the derivative with respect to t? And that, in this case, is this dr dt factor that you see here. Okay, so this says, if I was just going to kind of explain it in words, that the rate at which the volume changes with respect to time is 4 times pi times r squared times the rate at which the radius changes with respect to time. So that means that the rate at which the volume is changing is related to, I can write an equation saying how it's related to the rate at which the radius is changing. And it's that idea, the fact that the rate at which the volume changes is related to the rate at which the radius changes, that gives us this term related rates, which is this whole topic in 5.6. And sort of this is kind of like our big grand finale for first semester calculus. What can I really do with derivatives? Well, one really kind of important problem that we solve with derivatives is this idea, answering questions about how rates are related to each other. Here's how this is going to look most of the time for us. If I am interested to think about how the volume of this soap bubble is changing, I will get some kind of information about another rate that's happening or a certain measurement. So this is just a made-up scenario, but I could, if I happen to know that the radius is increasing, so the radius is getting longer at 0.1 centimeters per second, and if I happen to be especially interested in the moment when the radius is 10 centimeters, then I have enough information to say how fast the volume is changing at that time. So I would use, let's see, here's my original, here's the formula for the volume of a sphere. I've differentiated with respect to time to get an expression for the rate at which the volume changes with respect to time, dv dt. And I'm going to try to evaluate that expression using this information that I happen to have handy. So if this says the radius is increasing at 0.1 centimeters per second, that tells me that dr dt is 0.1 centimeters per second. So I'm going to replace dr dt with 0.1 centimeters per second. And I also happen to know that I care about when the radius is 10 centimeters, so I'm going to replace this radius with 10. When I do that, I have the 4 times pi, the 10 centimeters gets squared, 0.1, and if I do like what you do in physics and I multiply and divide all those units out, I'm going to end up with 40 times pi cubic centimeters per second. So what does that happen to mean? It's not that this is especially interesting maybe to us, but it tells me that at the exact moment when the soap bubble has a radius of 10 centimeters, if I was interested, the amount of air going in is about 40 pi cubic centimeters per second. And notice this, because this is going to be a big deal. Sometimes units throw students off here. But volume in this scenario is measured in cubic centimeters, because we're talking about a sphere whose radius was measured in centimeters. And time is measured in seconds. So dv dt, even though that's not actually a fraction, the units are going to have that same form. So volume units over time units. Notice our units here, cubic centimeters per second. So I hope you got a chance to fill that in. That's this first top problem at the top of your notes page. So the steps, I'm going to recommend these steps. The Those are bigger type, but they're a little bit abbreviated from the steps I want to use. So these come from your book with a couple of little annotations from me. If you're asked to solve a related rates problem, which you're going to start to notice because you're going to be asked a question about how something is changing at a particular moment. And especially if you're asked how something's changing with respect to some kind of variable, usually time, that is not the variable already in your function. So these steps, try to write down the rate you need, the rate you're seeking, and any rates you already know. And especially if you can write them using derivative notation, dv/dt or dr/dt, that's going to really help you piece together the equation you're going to need. Many related rates problems have a geometry aspect to them. So especially if that's the case, you might like to draw a picture. And you're going to use that picture then to help you write an equation. So your book says all this. Your book doesn't actually enumerate is exactly what kind of equation you're going to need. You're going to need to write an equation that is true based on the scenario. And it's going to need to include no derivatives. Even though we're going to need derivatives because we're looking for a derivative, like a dv/dt or a dr/dt, we don't want to start with an equation that contains derivatives. We're going to have to do that part next. So you want your equation to contain the variables whose derivative you seek and whose derivative you already know. So in that last example, we were looking for dv/dt and we knew dr/dt. So we started with an equation that contained v and r. Once you have that equation, which should be usually something from geometry, a volume formula or an area formula, or they're not usually obscure formulas. The Pythagorean theorem is a really common one to end up using. Once you have that equation, you're going to take the derivative of both sides of your equation, usually with respect to time. At the top of the page, I said that these are all to find a quantity, how a quantity is changing with respect to time. It's almost always time. But whatever it is that you want to find out with respect to, we're going to take the derivative of both sides with respect. And that's going to require implicit differentiation, which is why we just reviewed it. Once you've taken the derivative of both sides of that equation, you should have in your new equation an expression for any rate you already know and an expression for the rate that you're looking for. So in the problem we just did, we started with v equals 4/3 pi r cubed. Took the derivative of both sides with respect to time. So we had a new equation that contained both dv/dt, the thing we were looking for, and also dr/dt, a rate that we already knew. After you have that equation in place, then you can do what we call freeze the picture in time. It's not the case that the radius of that balloon was always 10, but there's a moment in time when it's 10, and we're going to freeze the picture then. If you try to freeze the picture before you take the derivative, you're going to end up taking the derivative of something that doesn't change. You're just going to end up with a bunch of zeros. So take the derivative first, then you're going to do your substituting. Once you have enough values substituted in that the only variable left is that rate that you're looking for, then you're just going to isolate that variable. If you can keep the units with all of your quantities, then you'll be able to figure out units at the end. Or the notation of that derivative you're looking for, we were looking for dv/dt, should tell you about the units. That's going to have units that are volume units divided by time units. All right, so I got one more example here, and then I'll change to the next video. Let's do this one. A spherical balloon is inflated with helium at a rate of 100 pi cubic feet per minute. So 2 questions. How fast is the balloon's radius increasing at the instant when the radius is 5 feet? Second, separate question. How fast is the surface area increasing at that same instant? So this is the part that really takes practice at the beginning. I have a balloon. At least I know it's spherical. I know some things about spheres. I probably know a formula for the volume. I probably know a formula for the surface area. What is this problem? What is problem A actually asking for? This is the first thing I'm supposed to figure out. So how fast is the balloon's radius increasing? The rate at which the radius increases is dr dt, so the derivative of the radius with respect to time. What quantities do I already know? I know a little bit about if I'm making my balloon get bigger. Notice the units here, 100 cubic feet per minute. This is volume over time. 100 pi cubic feet per minute is the rate of change of the volume with respect to time. That's how fast the size of the balloon is changing, specifically the volume of the balloon. So I've written myself some notes here. I am looking for dr dt, and I know dv dt. So that means I want to try to write an equation that contains v and r. So I've set you up here, so this isn't too big a leap. We already know a formula that relates the volume of a sphere to the radius. So I'm going to start with 4/3 pi r cubed. This is not going to be the formula we use every time, just this first couple of times. So I can take the derivative of both sides with respect to time, and I know that dv dt is going to equal 4 pi r squared times dr dt. That's that same derivative we already took at the beginning of the video. Now it's going to be time to freeze this picture. Mrs. Hicks, why didn't you draw a picture? Step 2 is supposed to be to draw a picture. I thought it was probably already clear how volume and radius were related. But feel free to draw a picture. Sometimes it helps to kind of make that connection for you. Once I have that equation, my dv dt equals 4 pi r squared dr dt, I want to remember the other things I know, and I'm going to freeze my picture. This was how fast is the balloon's radius increasing when the radius is 5 feet. So I'm going to replace dv dt. Right, so here's my equation that I start with. I'm going to replace dv dt with the 100 pi cubic feet per minute that was given at the beginning. And I'm going to replace r with 5 feet because I care about the moment when the radius is 5 feet. So I've left all my units on these quantities. You might decide that you want to leave the units off and figure out the units at the end. They're both good options. So 100 pi cubic feet per minute is equal to 4 times pi times 5 feet all squared times dr dt. So once I've replaced those, I don't have any variables left except this expression dr dt, and that's what I'm trying to isolate. So I'm going to do whatever math I need to do to isolate. Notice dr dt is getting multiplied by 100 pi feet squared. So I'm going to divide both sides by 100 pi feet squared. So my hundreds cancel, my pi's cancel, and I have cubic feet per minute divided by feet squared. That makes these all divided away to make 1 foot per minute. So the rate at which the radius is changing, it's increasing at 1 foot per minute. Part B, I have that. What's going on? Do I not have a part B for that? Here we go. So how fast is the surface area increasing at that instant? So I'm going to need a way to relate. Let me start with that. Okay, so quick reminder, we know that dv dt equals 100 cubic feet per minute, and we're interested about the exact moment when r equals 5. This time, we know something about we've been asked about the rate at which the surface area is changing. I'm going to call that ds dt. So we seek ds dt. We know dv dt. We just figured out dr dt, and we're interested in this moment when r is 5 feet. This is 1 foot per minute. So I'm going to need an expression that contains surface area and either v or So I'm going to go back to my catalog of geometry formulas and remember that surface area for a sphere is 4 pi r squared. Now I have an equation that contains s and r. I'm going to take the derivative of both sides with respect to time. So the 2 multiplies the 4 to make 8 pi r. I'm going to multiply by dr dt. So the thing I'm looking for, ds dt, is already isolated in my formula. I'm going to multiply 8 times pi times, now I can freeze my picture and let r be 5 feet times dr dt, we said at this moment, is 1 foot per minute. And I'm just going to simplify as much as I want. So in this case, ds dt, you might specify that I'm saying that this is when r equals 5, is 8 times pi times 5 times 1 makes 40 pi. Feet times feet divided by minutes is feet squared per minute. And notice that matches because surface area is measured in square feet, time is measured in minutes. So final answer, 40 pi, feet squared per minute.